ma'am, we shall start. Ready, ma'am? We'll start.
Yes, ma'am. I'm ready.
Good morning to one and all gathered here. A very warm welcome to this IEEE WIE Day celebration. Today is the 5th day celebration. We have been celebrating this event from last week, from 30th of June till 7th of July. We have planned, and IEEE is overall in across the globe. It is celebrating this WID celebration. So our college is also celebrating this from 30th of June onwards. And we were conducting many webinars, seminars, workshop, and then services to the outside community. So we have been doing a lot of celebration activities as a part of the celebration. So today we have this national webinar. Dr. Tanima Baumik from Kolkata. So a warm welcome, ma'am. Very glad to meet you here.
Thank you, ma'am.
So she has joined here. And this webinar is planned or arranged in collaboration with our Department of AA and DS. And we have a different center of excellence. I think you are also head of center. Yeah. So we have different centers in our college also, center of excellence. Okay. So center of AA, as your topic is very related to this AI topic. So center of AI, artificial intelligence, Mr. Ashok, professor of our department. So he has joined here. So first he will be briefing about that center for just for 2 minutes. So what are all the activities that has been carried out and what we are actually doing in our center activities. Just he will be briefing about that, and then we shall go for your session, ma'am.
Okay. Thank you, ma'am.
Thank you, ma'am. Thanks for the opportunity. Let me share the screen. My screen is visible here.
Yes, visible.
Yes, visible.
So we from RIT, representing the Center for Artificial Intelligence, here in our center that we make the motto as prescribed by Government of India. We pledge to position India as a Vishwaguru in AI, leading innovation, ethics, education, fulfilling our Prime Minister's vision on this. For this section, we will be dividing our center into 3 things. One is on responsible AI, second one is on computer vision, third one is on natural language processing. These are all the 3 divisions where students are working and faculty members are associated with them and developing the different variations of the outcome. With respect to our center that we have raised, here we have listed only 10, but cumulatively we have 34 patents. Among that, 8 are granted, and based on that, commercialization are in progress, as well as we have various MOUs signed with national and international MNCs and universities too. And we have list of publications in reputed journals. And these are all some of the projects that has been done by our students and moved for various arenas. Spinover, this project it's a complete rover. It has been made as a part of association with some of the inputs received from the ISRO advisors. And heavy vehicle detection, this is one of our students have involved with IIT Madras Research Park. He had completed this project and it has launched. It's a real view has been implemented near Anna Nagar West Depot, CCTV surveillance. And this is dystopian, that gamification of learning the curriculum that has been developed, as well as it's part of my PhD work. And drone detection, this is the one that we did for Indian Army. Actually, we have solved IDEX problem and we have moved up to 7 rounds of interview and we are waiting for further funding and process on this. And digital warehouse, it has been implemented in many commercial zones recently, and we have received a copyright grant for this product too. It is linked with inventory also, computer vision with inventory also. And this is the one that we have taken the statement from Smart India Hackathon, and we have solved this. In Uttarakhand, we have identified this Barasigiri glacier. So based upon the data received from the tropical department that we have constructed, and this equation is currently running, and it is producing the exact way of melting. Even you can scan this and you can check the current status of the melting rate, actual data provided by the department, and the thing what it is guessing also will come aligned with the values. And this is also another level of gamification for learning programming languages like dystopian. And this is an interesting one that we have associated with the NIOT, Chennai, National Institute of Ocean Technology, related to identification of underwater archaeology. So initial stages of the work has been submitted for NIOT proposals. And these are all some of the things that we did. And still we have some more achievements with respect to Corporation of Tirupur. We have submitted our CC-based application, and really nearly 23 use cases we have solved and we have submitted. We compete among 25 startups. We secured a second position in that, and we bagged the MOU with the Corporation of Tirupur, especially Smart City Corporation, Government of India. And this is the set of our student members from our center. They have participated in Innal Unnati Grand Challenge, and they have received a first runner-up with a cash prize of 50,000. So this is a set of students who have participated in the hackathon. So we have the regular practice of participating in hackathon organized in private firms, and making our students to expose to the real world problems, as well as we are making our students to participate in international AA competitions, specifically targeting coined by the major MNCs, especially Walmart, Amazon, etc. So likewise, we are doing consultancy also. So if on requirement of any consultancy related to training, development, and related to research, we are ready to collaborate and work. Thanks for the opportunity, ma'am.
Nice.
Thank you so much, Ashok. It's a very nice, brief introduction and explanation about the Center of AI. Thank you once again. And I take this opportunity now to introduce our chief guest today as a resource person for this national webinar. Dr. Tanima Baumik is a passionate educator, researcher, and innovator, currently serving as an associate professor and head of the Center of Excellence in Advanced Communication and Intelligent Computing at the Institute of Engineering and Management, Kolkata, India. With a rich academic background in wireless sensor networks assisted IoT field, she has made impactful contributions in areas including artificial intelligence, machine learning, robotics and embedded systems, and intelligent automation. As an active senior member of IEEE, she is also an ExCom member of IEEE Kolkata section and a dynamic mentor. Dr. Baumik has guided numerous student teams to success on international platforms, most notably at the IEEE Region 10 Robotics Competition 2024 in Tokyo, where her team secured global recognition. Congrats, ma'am. She also serves as an ambassador for IEEE WIE Day, reflecting her commitment to empowering women in engineering. Her recent accolades include winning the first prizes at the IEEE Dataport Healthcare Hackathon, Big Pitch Competition, FLEPS 2025, REF Cold 2024 Innovation Contest, and the ISHAR Innovation Challenge with projects that promote sustainable technology and social impact. She is deeply involved in collaborative research initiatives, MOUs with premier institutions, and has played a key role in establishing research and development infrastructure. Dr. Baumik is known not only for her technical experience, but also for her community engagement, working for underprivileged children and promoting STEM education. She continues to inspire with her vision of using technology for societal betterment. So I hope I have called the right person for this day. Women in Engineering Day. So very proud and very happy to see your profile, ma'am. You have done a lot.
Thank
And
you.
you have
It's my privilege.
contributed a lot to the society and as well as for the students and faculty members also. So over to you, ma'am. We are all waiting for you to hear your session.
Yeah.
So participants will be seen through the YouTube live link. So you can start your session, ma'am.
Okay.
Over to you. Thank you.
May I share my screen, ma'am? Now I share my screen.
Yeah, you can share.
Okay, okay.
Visible, ma'am.
Ma'am, is it visible?
Yeah, visible, visible.
1 minute. Is it visible now? Okay, okay. Ma'am, is it visible? And
Yeah, visible and
okay,
audible, ma'am. Please
okay,
continue.
okay, okay. Good morning, everyone. Thank you, thank you. It's my privilege. I am Dr. Tanima Bhumi, and it's my privilege to discuss a topic that lies on the intersection of the innovation and necessity, digitization and AI for precision agriculture and smart farming systems. As an associate professor in computer science and engineering with the specialization in AI and machine learning, my journey has consistently focused on how we can harness this advanced technology to tackle the pressing challenge in the agriculture sector. Today, I will deep into how digital transformation and AI are fundamentally reshaping the farm, manage the resources, and feed our population sustainability. First, coming that point, the agriculture continues to be the backbone of our Indian economy, employing a large percentage of our rural population and contributing significantly in our GDP. However, traditional farming methods are no longer sufficient in face of climate change, population growth, and depleting the natural resources. This is where the digital tools and AI come in. Smart farming integrates the sensor, drones, and data analytics to transform the agriculture practices. This technology not only enhance the productivity but also contribute directly to the several sustainable development goals, including no poverty, zero hunger, sustainable communities, and responsible consumption. By adopting AI, we aim to maximize the yield while minimize the input waste, providing farmer with real-time data, driven insight, and support the better decision making. The objective is to empower the small and marginal farmer with tools that align the technology with national development goals. As we move forward, we must continually monitor how digital agriculture influences our yield, reduces the input cost, and provides the early risk alerts and ultimately uplift the rural communities. Next, coming that point, I discussed about to understand the transformative impact of digitization and AI on agriculture. Firstly, I explored that how this technology is revolutionary farming practices by enabling the data driving decision and transition from traditional methods to precision agriculture. Secondly, we look into the key components that make the smart farming, including the IoT sensor, drone, machine learning algorithm, cloud computing, and mobile application that actively engage the farmer. Thirdly, we will try to delve into the real world application where AI is being used for pest detection, crop planning, soil monitoring, and leading to improve the yield, cost saving, and obviously sustainable outcomes. So finally, we will try to examine the current trends such as regenerative agriculture, blockchain, and vertical farming, as well as the ongoing challenges related to the technology adoption and data privacy and infrastructural graph. Next, coming that point, next slide. This is basically the advancement we see today. We must reflect on how agriculture has evolved. During the Green Revolution in 1960s and 70s, India saw a massive increase in the food production through the use of high-yield variety seeds, chemical fertilizer, irrigation technique. While the revolution prevented the famine and bolstered the food security, it will also lead to overuse of the natural resources, soil degradation, and long-term environmental damage. In contrast, today we are experiencing the digital revolution where the emphasis is on sustainable, efficient, and climate smart farming. The focus has shifted from increasing output by any means necessary to optimizing the input through precision technology such as IoT, satellite imaging, robotics, all driven by the data and AI. Next come that point how the evolution of the agriculture process from our ancient dragging stick to now in the precision agriculture. This is basically the difference in between the green revolution and the digital revolution. Here, it represents that the former relied heavily on the physical input, the latter thrives on the digital intelligence. The Green Revolution addressed immediate food scarcity, but did so at the cost of long-term sustainability. In contrast, the digital revolution is geared towards the precision using of data to guide every decision from seed selection to harvest timing. This shift not only aims to increase the productivity but also ensure the health of our environment and resilience our agriculture systems. Now coming that point, the agriculture 4.0. It signifies a paradigm shift in farming powered by the cutting-edge digital technology, automation, and enhanced connectivity. This future-forward concept emphasizes the precision and sustainability, aiming to produce more food with fewer resources. Whether it reducing the water and chemical uses and improving the crop quality and environmental health, the goal remains the same, smarter farming for better tomorrow. The technologies such as AI, IoT, robotics, big data, drones, all are basically backbone of agriculture 4.0. They allow for real-time monitoring for crops, soil, water, and climate, enabling a continuous loop of sensing, analyzing, predicting, deciding, acting, and learning. The applications are vast from AI predicting pest outbreak to IoT sensor monitoring soil condition and drones automatically seeding and harvesting. All these advancement covers to support the broader goals of sustainability and farmer empowerment, especially for those in the remote and resource constant environment. Now I come to explain about the key technology of AI, deep learning, machine learning, and big data. AI is basically the broad concept of machine mimicking human intelligence, including reasoning and problem solving. Machine learning is the subset of AI that enables system to learn from the data and make decisions without explicit programming. The deep learning takes this a step further by using the natural network to analyze the complex data such as images, videos, and making it particularly useful in the agriculture for disease detection and yield forecasting. The big data, characterized by the volume and the velocity and varieties, provides the raw material of these models need to function. Collectively, these technologies empower us to make smarter decisions in real time, tailored to each farm unique collection. Smart decision-making loop in Agriculture 4.2 encapsulates how technology transforms the raw data into actionable insight. It begins with the sensing where data is collected via drone, satellite, and IoT sensor monitoring the various field parameters. This data is then transmitted to the robust IoT network to cloud platform where machine learning model analyze the pattern and predict the future outcomes. These insights help in making informed the decision such as when and how much to irrigate or which area need pest control. Actions are then executed either manually or through automation, and the outcomes are continuously monitored to refine the future decision. This loop ensures a continuous cycle of learning and improvement, enhancing precision and sustainability in every farming activity. Now coming that point, the precision agriculture. Precision agriculture is the modern farming method that uses technology to observe and respond to variability in the field. By gathering data on soil health, crop performance, weather condition, farmer can make data-informed decision to optimize the resource use and maximize the yield. This approach not only increases the productivity but also minimize the environmental impact. The key components include monitoring tools such as drones and satellites, analytical models driven by AI and machine learning, and controlling the mechanism like automated irrigation systems. Unlike the traditional farming, which often treat entire field uniformly, precision agriculture tailored the intervention to specific zones, ensuring that resources are used where and when they are needed most. Now, obviously coming that point, what is the default in the traditional farming, and now we come in the precision agriculture. In traditional agriculture often involve generalized practices that do not account for the variability within the field. This led to low productivity, high labor requirement, and inefficient use of resources. Problems like pest infection, poor soil health, erratic weather, and often a days too late due to the lack of real-time monitoring. So that because we come in that precision agriculture, which are the problem statement, these all things. So now coming that precision agriculture leverages the real-time data and AI-driven insight to provide timely alert and recommendation. It reduces the dependency on manual labor, prevents outuse of the fertilizer, which basically cause the climate problem, and pesticide. It enables also better planning and execution. That is our motto in the precision agriculture. This transformation is essential for building a resilient and sustainable agriculture systems that meet the need for the present without compromising the future. This is basically the proposed solution in our project. We have to include it. In response to these all challenges, we propose that in smart agriculture drone system integrated with the DEW nodes. These systems use a drone for aerial surveillance and data collection, while the DEW nodes monitor the ground level soil condition like the soil moisture, pH, and nutrient content. These components work together to provide a comprehensive view of field, enabling the targeted intervention. Data from the both sources is clustered and analyzed in real time to deliver the precise recommendation for irrigation, fertilization, and pest control. This integrated systems is designed to be cost effective, easy to deploy, and scalable, and making it ideal for the small and marginal farmers. These are basically smart agriculture drone and dew nodes. The smart agriculture drone and dew node system is a technological solution designed for both aerial and terrestrial data collection. The drone component is equipped with high resolution camera and multispectral sensors, allowing it to capture the detailed image of the crop field from above. This image helps in identifying the crop health, detecting the pest infection, and monitoring the overall growth. On the ground, the dew nodes are embedded with sensors to monitor the soil parameters, just like pH, moisture, temperature, nutrient level in real time. These nodes are connected via wireless communication protocol, sending data to the central server for further analysis. This dual layer approach ensures a holistic understanding of the farming environment. The combination of the drone imagery and dew node sensor data form basic of predictive analysis and precision farming, enhancing the decision making and farm productivity. The architecture of the smart agriculture drone is structured in efficiency. Just like here, the adaptability and autonomy features onboard process that allow the preliminary image analysis before data is transmitted. So this basically reduces the load on the central server and speed up the decision making. The drone is designed with modular frame to accumulate the various sensors, including the RGB, thermal, and multispectral cameras. It uses the GPS and 1 minute. Basically, drone reduces the load of the central server and speed up the total decision making. The drone is designed with modular frame to accumulate various sensors, the RGB, thermal, multispectral camera. It uses the GPS and GIS data to follow the predetermined path while covering the entire field area with accuracy. The real-time communication is maintained through MQTT or similar low latency protocol. The data collected is encrypted and transmitted to the cloud platform or edge computing devices for further AI-driven analysis. These architectures support the plug and play compatibility, making it easy for farmers to update and customize the drone with additional modules. This makes the drone a flexible tool capable of adapting to different crop type and farming environment. During the autonomous flight testing, the drone demonstrated its ability to navigate the complex farm topology without human intervention. It also able to take off, survey the designated plot using the onboard navigation systems, capture required data, and return safely. The autonomous systems uses the real-time kinetic positioning for precise navigation, reducing the margin of error to just a few centimeters. The obstacle avoidance algorithm implemented through the LiDAR or ultrasonic sensor ensured that drone could navigate safely even in the uneven or cluttered environment. This test validates the drone efficiency and reliability, making it a valuable solution in continuous agriculture, surveillance, and monitoring without requiring the skilled pilot. The success of this test highlights the drone potential to revolution in remote farm management, especially in the region with labor shortage. So digitization in agriculture also play an important role, just like it can transformative role to facilitating the seamless collection and analysis and application of the data. Sensor and drone are the primary tools used to gather the real-time information from the farm. The IoT-based sensor track the soil moisture, humidity, pH level, and nutrient content, providing the continuous update and that allow for timely intervention. Drone capture the aerial image that helps to access the plant health, detect early sign of the disease, and monitor the crop growth. The integration of satellite imaging enables the large-scale monitoring over extended period, identifying the changes in the vegetation and supporting the dot assessment. The digital platform compile all this data into intuitive data board, enabling the farmer to make data-driven decisions. This platform also provides the mobile application that deliver the localized or recommendation, market update, and alert directly to the farmer smartphone, bridging the information gap between the technology and the end user. Here, basically, I mentioned the technology behind the digital agriculture. The satellite imagery has emerged as a powerful tool in modern agriculture, offering the bird's eye view of the farmland on an unprecedented scale. With satellite data, we can track the vegetation indicators, monitor land use changes, and identify the sign of the crop stress well before they became visible to the naked eye. These insights are invaluable in accessing long-term trends and planning the seasonal activities such as sowing and harvesting. The satellites support the yield prediction and dot assessment by analyzing the variation in the temperature, soil moisture, and plant fertility across the large region. By integrating this data with onboard sensor input and drone imagery, we create a comprehensive multi-layer understanding of the farm ecosystem. The high-level monitoring not only aids policymakers and researcher, but also benefit the farmer by providing macro level information that complements their field level insights. Here, we see that the digital platform and dashboard act as a nerve center of smart farming. They integrate the visualized data collected from the various sources, including sensor, drone, satellite, and weather station. These platforms are designed to be user-friendly, making it easier for the farmer and decision maker to track the real-time condition and receive the actionable recommendation. Custom dashboard allow user to monitor the specific parameters such as soil moisture, pest risks, nutrient level to generate the alert when thresholds are raised. Moreover, AI-driven analytics enhance this platform by offering the predictive insight on the crop performance, potential trait, and optimal input schedule. The mobile application connected to this dashboard ensure that farmer can access this insight anytime and anywhere. By simplifying the complex data set into visual format, digital platform empower the stakeholder at all levels to make informed and timely decisions. Now coming that point, the similar advanced technology covers it to form the backbone of our digital agriculture. The Geographic Information System, GIS, help in mapping the land features, analyze the soil type, and studying the historical yield pattern. These insights support the zone-based crop planning and resource allocation. GPS, global positioning systems, also aid in the precision seeding and field navigation and guided the machinery operation and minimizing the human error and increasing the efficiency. The cloud computing facilitates the storage and analysis of massive volume of agricultural data, enabling collaborative decision making, and remote monitoring. Furthermore, mobile applications serve as a vital interface between the technology and the farmer. They deliver crop advisory, market price, weather forecast, pest alert directly to the users' phones and ensuring the quick access to crucial information. When combined, this all technology transformed the traditional farming into smart, integrated, highly responsible farming systems. So that because now we are coming that point, the AI-based smart farming system. Ma'am, is it okay? Ma'am, hello. Any question?
Once again.
Any question, ma'am?
Any question? Just I'll check it out.
Okay, okay. Then I go.
It's a completed or still it's there?
No, no, no. Still we have.
You
Yeah,
continue, ma'am.
because
So,
okay,
as of now,
okay.
no questions.
Okay, okay, okay.
Okay.
Is there any question arises? Please
Yeah. I will
tell
ask
me
at the
because
end
at
if
a
any
time
question
I am
comes.
not sure any question here, so that because I
Yeah. At the end, I'll tell. Participants, if you have any question, you can type in the chat box in YouTube. You continue, ma'am.
okay, okay. Thank you, thank you. Okay. So AI holds the transformative potential in agriculture because it introduces a level of intelligence and adaptability that traditional systems lack. Through predictive analysis, AI can forecast the crop yields, pest infestation, the weather anomalies, allowing the farmer to plan ahead and reduce the risks. AI systems analyze the vast dataset to offer insight that would be impossible to detect manually, such as changes in the plant health or evolving the weather trend. Real-time decision making became possible as AI algorithms integrate the sensor data and environmental conditions to trigger the automatic response like irrigation or pesticide application. Beyond of this, AI system continuously run and improve with each cycle of the data, delivering personalized recommendation based on the farm's unique condition. This ongoing refinement enhances both the short-term productivity and long-term sustainability, making AI not just a tool but an essential partner in the future of the farming. Okay. So these are also the part of the AI technique which are used in our smart agriculture system. So first coming that point, the machine learning. Machine learning play a vital role in smart agriculture by enabling system to learn from the historical and real-time data to make accurate prediction and recommendation. For instance, using data on weather pattern, soil condition, or crop varieties, machine learning algorithm can forecast the yield potential or likelihood the disease outbreak. This proactive approach allows the farmer to take a preventive measure well in advance, reducing the losses and optimizing the input. By continuous updating itself with new data, the machine learning model became increasing accurate over time and adapting to changing the environmental conditions and farming practices. This makes it a powerful tool for managing variability in the crop production and ensuring more stable outcome across the different growing seasons. The computer vision is transformed how farmers monitor and interact with their crop by enabling machines to interpret visual information from images and videos. By deploying the cameras on drones, fixed stations, and mobile devices, computer vision system can detect early sign of the pest, disease, and weed infection. These systems are trained to identify the specific pattern and anomalies, allowing for the highly targeted intervention. Suppose computer vision can distinguish between crop and weeds, guiding the precision spraying and reducing the herbicide uses. It also helps in identifying the stages of the crop goals and detecting anomalies in the plant health, enabling the timely action. The ability to analyze the visual data at scale accurately and consistently makes the computer vision a cornerstone of next generation agriculture diagnostics. Sorry. Deep learning also takes machine learning a step further by using the multi-layer neural network to model the complex data relationship, particularly in image and signal processing. In agriculture, deep learning excels at tasks like diagnosing plant diseases with leaf image or accessing the food ripeness from the color and texture analysis. This model can process vast amount of image data and learn instinct pattern, offering a level of diagnostic precision and reveals the human expert. Reinforcement learning, on the other hand, is especially valuable in the dynamic environment like greenhouse or autonomous tractors. It learns through the trial and error and adjusting its strategies based on the environmental feedback. Suppose a smart irrigation system using the reinforcement learning can learn to adjust water delivery based on the changing of weather and the soil condition, improving water use efficiency over time. So together, all these AI techniques provide a powerful tools for building responsive, adaptive, and intelligent agriculture systems. These are the other tools, smart farming tools are used here. So these are drone that are equipped with high resolution and multispectral camera offer detailed aerial map that help in terrain analysis, crop health monitoring, and yield estimation. These tools are invaluable for field segmentation, allowing for the customized treatment of each zone based on its unique characteristics. Soil sensors play an equally vital role by continuously monitoring the parameters such as moisture level, temperature, nutrient level, just like NPK level. This data is critical for optimizing the irrigation schedule and fertilizer application, thereby enhancing the plant health and reducing the input waste. The integration of AI into irrigation systems hold the great promise. These intelligent systems will automate the water distribution based on real-time soil and climate condition, cutting down on water and energy use while ensuring the crop receive exactly what they need. Collectively, these smarter tools form a interconnected network that empowers the farmers to manage their field with a level of precision and efficiency that was previously unmanageable. This is the picture here. Basically, it's a framework of smart farming system to build on a cohesive integration of sensing, data analysis, and decision making, and obviously actuation. It begins with the data collection through advanced tools such as drone, soil sensor, weather station. This data is then analyzed using AI and machine learning model to extract the actionable insight. The system identified the early sign of the pest infection, the recommendation suitable crop for given soil and climate condition, and classification weeds for targeted treatment. The leaf disease detection models utilize the deep learning and aerial imagery to provide the accurate diagnosis, while livestock monitoring system ensure the animal health and movement are tracked in real time. So each component of this framework feeds into a centralized platform where farmer can visualize the information and act upon it. Whether it's deploying the pesticide, irrigating the particular zone, or choosing the next crop cycle, the smart farming framework ensures that every action is evidence-based and resource optimized. I already explained this type of application basically included in the smart farming systems. So now I basically explained some of the use case with respect to AI-based smart farming systems. So first coming that point, AI-based irrigation systems. So this system irrigates the soil moisture and temperature sensor with a custom-built machine learning model to predict when and how much to irrigate. The sensor constantly monitors the field condition and the model processes this data to determine the optimal irrigation schedule. Once the decision is made, the irrigation pump is automatically activated or deactivated, ensuring that water is delivered precisely when and where it is needed. The outcome is a fully automated irrigation process that drastically reduces the need for manual intervention. By adapting to the soil and weather condition in real time, the systems minimize the water and energy waste and ensure the consistent crop health. Farmers have reported up to 30% reduction in the water consumption compared to the traditional method, and demonstrating that intelligent irrigation is both economically and environmentally beneficial. Next, I also explain these are also part of the AI based. Then I use the use case 2 for pest detection. Our model built on the YOLO V9 algorithm. YOLO, that means you only look once, is a state-of-art object detection model capable of identifying the pest-related anomalies in the real time. The system scans the leaf image for sign the disease spots, the pest presence and damage pattern, allowing the farmer to act before the infection spread. This technology enables the early intervention, helping to lower pesticide use, reduce the crop loss, improve the farmer decision making. It also minimizes the reliance on the manual spotting and expert consultation, making the pest management more accessible and cost effective for small scale farmers. Overall, the integration of AI into pest detection has proven to be game changer in the proactive crop protection strategy. These are the outcomes by using AI-based pest detection technology. Next, coming that point, the another use case that is for leaf disease prediction, where AI has shown remarkable impact. In these systems, a mobile application allows farmers to capture image of infected leaves using their smartphone. These images are analyzed in real time by a deep learning model built on YOLO V9, which has been trained on a diverse dataset of leaf disease affecting multiple crops. The model instantly identified the type of the disease, assesses its severity, and recommended appropriate treatment option. In addition, the application maintained a history of result and include a alert that include alert in the farmer. The greatest advantage of this approach is that farmer can receive expert level diagnostic without need for the physical consultation. Field trials have demonstrated the app effectiveness in detecting the common diseases such as blight, powdery mildew, which are basically caused in the rice diseases. So it can easily early diagnostic, and we can take the targeted actions accordingly. These are the outcomes basically by using this pest detection method. The another part is the crop recommendation systems that can significantly improve both productivity and sustainability. Our proposed model uses hybrid of decision tree and random forest algorithm to analyze the various parameters such as soil pH, moisture content, nutrient level, and local weather condition. The model then suggests the most suitable crop for a specific field and obviously the season, considering the historical yield data and real-time soil assessment. These systems ensure that crops are well matched to their growing environment, minimizing the input waste and enhancing the yield. During the field deployment, this model achieved over 97% of accuracy, closely matching the result from the laboratory soil test. The recommendations were well received by the farmer who observed the better crop health and increased the returns. This use case highlights the role of intelligent planning in reducing trial and error approach and empowering the farmer with data backup decisions. Okay. So, these are basically the crop recommendation output we got, and we already published in the paper all these things. Next, coming that point, the pest detection and crop weed classification. So it is also crucial for sustainable farming. And this use case example the application in the real-time image analysis. Using the drone acquainted imaginary and YOLO V9 model, the system distinguishes between the crops, weeds, and pests in the field image. Once detected, the information is being used to execute the precision pesticide or herbicide spraying, targeting only the affected zone. This minimizes the use of the chemical and protect the beneficial flora and fauna also. Additionally, it reduces the overall operational cost and labor. The model ability to process the high resolution images quickly allow for the large field coverage in a short amount of time. This automation and accuracy enable more environmentally responsible farming practices while maximizing the crop production. Another thing is very, very important, which is the livestock monitoring. In this case, the drone surveillance integrated with YOLO V9 and object tracking algorithm was used to monitor the cattle movement and the health of this cattle also. The system tracked individually animals, identified any anomalies in their behavior, and ensured the herd integrity. If an animal separate from the group of show the sign of the distress, alert are triggered for immediate action. And the remote monitoring reduces the need for the constant human supervision and ensures better health outcome for the livestock. Farmer using this system reported improved the herd management and efficiency and reduced the mortality rate and enhanced the resource planning. This technology brings a layer of intelligence to livestock care that align with the overall goal of the precision agriculture. That means do more with less and do it more better. So these are basically output of the pest detection and the livestock monitoring, all these things. Now I show you my project of drone, which is already using the test cases, field testing. Okay, so the result from our real world deployment reflects the tangible impact on the AI-powered farming tool. Across our various models, pest detection, weed classification, livestock tracking, and disease resistance, observe the substantial improvement in the farm operation. The time spent on the field inspection are reduced by 65%, allowing the farmer to focus on more strategic tasks. The usage of pesticide and fertilizer dropped by 30 to 40%, and crop will increase by 18 to 22%, primarily due to better crop soil matching and proactive treatment. The real-time monitoring of the soil moisture also prevented the over-irrigation, conserving water and preserving the soil health. Moreover, the deployment of low-power IoT devices and optimized drone path minimize the energy consumption, further contributing to the environmental sustainability. This outcome reinforces the fact that when technology is properly aligned with the farmer needs, it leads to measurable improvement in both productivity and ecological responsibility. Basically, these are the target beneficial for our AI-based farming management systems. I think I am near to the time now, ma'am. Okay, I am just go move forward. Okay. These are basically for business model. We are analysis different type of startup or drone system who are already proposed their systems with our model. We have to try more smarter and uh, more responsible devices by using our method. Okay. So these are basically comparative survey with the other model. Acha. With the market size estimation, basically we are thinking that if we are just given our drone with respect to maybe subscription model or maybe in marketing. So if we market our drone in that time, it cost approx 464.8 US dollar. And for div node, we make this div node, it's approx 46.48 US dollar. And if they see even specifically in our West Bengal, our farmer are not afford all these things. So that because we are trying for the subscription model here. So if we are using the subscription cost without UAV, it's 34.86 US dollar, and subscription cost with UAV, it's 162.68 US dollar. Okay. So these are basically one of the most significant benefits for integrating AI and digital technology into agriculture is the dual impact of the operational efficiency and environmental conservation. So traditional practices often result in excessive resource usage and contributing to the soil degradation, water scarcity and pollution. So with smart farming systems, so every input be in water, fertilizer, pesticide is used precisely only and when needed. The efficiencies translate to reduce the cost and better crop health and lower the environmental impact. So next coming that point, these are the sustainable development goals which we try to achieve through our AI-based digital agriculture systems. So I think I already mentioned no poverty, zero hunger, sustainable cities and communities, and responsible consumption. Okay, these are our motto to try this SDG goal to achieve all these SDG goals. India basically actively forecasting the integration of digital technology into AI through several nation initiatives. Suppose ENAM, which platform is National Agriculture Market, enables the transparent and pan-India electronic trading of agriculture communities. This initiative has improved market access and fair pricing of the farmer. The ISRO crop monitoring system leverages the satellite data for accuracy estimation, dot assessment, and yield forecasting for the policymaker and individual farmer also. The Digital Agriculture Mission 21-25-6 to unify the data system and implement the technologies such as AI, IoT, and blockchain across the agriculture ecosystem. So additionally, mobile application like Kishan Jantro, Kishan Shubide provide the rural user to access the machinery booking, weather update, and market rate also. These are basically the challenges we face for our smart agriculture system, the major issue is the lack of high quality localized data, which hampered the performance and relevance of the AI and machine learning model to diverse the agroclimate zone. Many farmers also struggle with digital literacy, limiting their ability to effectively use the technology-based solution. The infrastructure gap also in the rural area poses another barrier. So poor internet connectivity, unstable power supply can prevent the real-time data access and disrupt the device functionality. And the lastly, I say that ethical concern around the data privacy, ownership, and consent must be carefully managed. Farmers should have to control over their data, and governance framework must be transparent and inclusive. Addressing these challenges requires a multi-stakeholder approach involving the government, the academia, technology developer, and farmer cooperatively to ensure that digital agriculture is not only innovative but also equitable and trustworthy. These are the future trend. We try to our smart farming system. Obviously, we try to use the digital twin in our farmland in future, and also we try to use much more robot or robotic things in our smart agriculture system in future. So these are basically my all part of summary that how digital tool and AI are transforming the agriculture from monitoring crop to predicting diseases to smart farming, improve the yield, reduces the waste, support the sustainability, but we must work together just like government, tech expert, farmer to ensure the adoption in widespread and fair. So let's move forward with smart farming as a shared goal for better future. These are particularly the publication which is connected with AI-based agriculture I mentioned here. So thank you. Thank you, ma'am, for giving me the opportunity to explain my work here.
Thank you. Thank you so much, ma'am. Very nice. You have given a brief introduction and overall about the complete, implementation and applications of AI, machine learning, deep learning in agriculture and how smart farming has been done and identification of diseases using pests, drone, all areas you have covered. You have given a broad overview to all the participants. It was a nice session actually. And I think no questions in the chat box as of now. There is no questions there. So in YouTube I saw. So publication, our students also, we also did like tomato plant disease leaf identification. So that was published in a journal also just 2-3 years before. So very useful. The smart farming and application of AI and machine learning is really very useful. So no questions as of now, ma'am. All just participating only. So I take this opportunity to propose my vote of thanks. Heartfelt thanks
May
to
I
you.
stop the PPT, ma'am? Now, stop my PPT.
Yeah. You can stop. You can stop sharing. Okay. So I take this opportunity to propose my vote of thanks to our chief guest today, Dr. Tanima Baumik from Kolkata. So very nice of you, ma'am. And I thank my our management, our principal, Dr. Maheshwari, and all the faculty members and of our college and students of our college, IEEE members who all actively participated in this webinar and all in these 1 week sessions. And feedback form for all the participants will be posted in the WhatsApp group. Already those who are registered for this session, you all were joined in a WhatsApp. So in that group, feedback form will be posted. So all can fill that feedback, and certificate will be issued either today or just as it is a weekend. You please be patiently wait by today or by Monday. Maximum by Monday, you all will be getting the certificates for all the participants will be giving. On Monday, we have a soft skill development physical mode. So we have called an corporate trainer for soft. It's an actually SPX sponsored IEEE SPX even. So that comes to the conclusion of our 1 week celebration, the women in engineering. So 1 week we celebrated. So nice of you, ma'am. Thanks a lot again. So just last week only I approached ma'am, just 4 5 days before only I called you, I think. So readily you accepted, and after and till 9:30 also ma'am said she has class. So after completing the class after 9:30, her come and join here. So thanks a lot, ma'am, again.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, ma'am. May I leave? May I
Yes,
leave the
ma'am.
meeting?
Can sign off. Sign off. Thank
Okay,
you. Thank you.
okay. Thank you.